I first want to say it's a great pleasure to be speaking here to this conference in the honor of Greg Lawler. So I've known him for many years. I'll come back to that in a moment. And it has been very stimulating having the chance to discuss with him and profit from his great knowledge. I sat and tried to figure out when was the first time I met him, and I'm still not quite able to figure that out, but remains in my mind a conference which was in the mid-80s in Arizona, and where there was also Gordon Slade, and there were also people from Turbulence who were there, and it was in Phoenix, I think, no, Tucson. And that was a very interesting meeting, very lively, and as often in Turbulence, extremely lively to the extent that people were explaining to some doing simulations that they were simulating the wrong thing. And we probabilists came out as a rather peaceful and nice crowd in a way. And I remember being on the way back at the airport, and suddenly came Greg, and so we had a nice chat there, and there was also Gordon Slade. We were all waiting for planes, so it's quite a lovely memory I have from that time. And for those of you who wonder, yes, in the mid-80s, people were using air travel already at the time. Yes. Okay, so well, it's great to be talking here in this conference, and let me get on with my subject. So, so a motivating problem for what I'm going to talk about, it's the question of how to think of the way a simple random walk is able to insulate or disconnect from infinity a large macroscopic body. So, so motivating problem corresponds to looking at the simple random walk, and you look at the trace it leaves. It's on ZD. So it's trace. And you look at its vacant set, so the sites not visited. And you have a macroscopic body which is modeled on something. So for the purpose of my what I'm going to talk about here, a big box in RD is good enough. And you are just looking at discrete blow-up of that model compact set. So it's and the type of question that you want to understand is you have a simple random walk starting from the origin. There is this big macroscopic body which is there, and you want to have some understanding of the probability that you cannot reach infinity when starting from that macroscopic body without meeting the trace of the random walk. And what's the behavior of that? Well, of course, if you are taking d equal 1 or 2, in that case, the probability that somehow the random walk is insulating that big discrete box is 1, because it's just a recurrent guy, so the p is 1. But if d is bigger or equal to 3, well, it's a bigger chunk that you have to somehow insulate. And the type of question is, well, you first can guess that it's plausible that this is tending to 0, but then how? Okay, so this is essentially the type of the topic I want to talk about here today. Now it turns out that to discuss that, it's very useful to have something which is in storing their translation invariance. You see, the problem I discussed is very non-translation invariant. The origin plays a role, and so you want some structure to describe what happens locally. And this is the role of what came in the title, so these random interlacements. So my goal is absolutely not to start to unfold all that is known and you never wanted to know about random interlacements. I just want to gather here a few facts that I'll use later on. So there is one quick way to define the random interlacement at level U. So it's just, so U is a positive number, so it's just to have it as a random set in ZD, and here with D bigger or equal to 3, which will be IU, and characterized by the property that the probability that this IU guy misses a finite set in ZD, so as a formula, which is e to the minus u, the capacity of that k, and that's for all k, which is finite in ZD. So this is a very quick way to introduce and characterize that set, which is translation invariant. You can start to read off things from that formula, but somehow, even though it's very quick, it's somewhat non-transparent, and I'll give in a minute a different way to do it. But just for the sake of being definite, so this capacity, it's the discrete capacity, so it comes as the infimum as the energy of a function phi which is bigger or equal to 1 on k and which is finitely supported. And here, just to be fully definite, it's sum for x neighbor of y, and I have that normalization of phi y minus phi x squared. So that's this energy which I'm talking about. So there is another way which is quite convenient to describe this, which is the Poissonian description. And one quick way to get about it is you are taking some finite portion of space, some box C, and if you want to realize that IU inside C, so what you do is you start to pick points on the boundary of C with a Poissonian distribution, which is U times the equilibrium measure of C. Okay? So what that means is that you are here something where each point on the boundary has an independent Poisson random variable, and its parameter is this U, the U which is from here, times EC, and EC is this equilibrium measure, and it can be seen as minus discrete Laplacian of phi, where phi is the optimal guy for this. So the optimal for the capacity variational problem attached to C is a phi. Of course, that phi is not finitely supported, but it's harmonic outside the box. It's 1 on the box. It's superharmonic. Minus Laplacian of phi is a measure, a positive measure. And this is what you are just using somehow to draw points on the boundary. Okay, so there may be two points sitting at the same location. I don't want to have too complicated a picture, but once you have that, you just take walks starting from there, from these points, so there may be several walks, and because we are in dimension bigger or equal to 3, at some point these walks are living forever this box C. Now what happens is that what you have drawn inside the box is just a realization of IU intersected with C. And if you want to get IU, so you just let C tend to infinity. So you let the, or rather to ZD. So you let this box grow. So this is a quick way to get a grasp of what it is about. There are much more elegant way of really defining globally with no limit whatsoever what the model is, but this is irrelevant for what I want to talk about. Okay, so this is the interlacement at level U. For us, it's going to play the role of a local Gibbs measure. It will describe things in kind of what's the microscopic world looking like. The other thing that I just want to mention, you see this parameter U is such that as U increases, you get more and more of these trajectories, so somehow your set is becoming bigger and bigger, and to the point that when U tends to infinity, it's invading the whole space, and you have the measure of this coming back, or the flip of that phenomenon coming back in that formula. You see when U is 0, this probability of missing something is 1, but when U tends to infinity, if that K is something which has a point at least, so this is tending to 0, so you are filling space with this cloud of trajectories falling down more and more. Okay. Now, the next piece of information that I need somehow here is to recall a bit about these percolative properties. So there are two sets here which play a role. So there is IU, and there is this complement VU, which is the vacant set. And what happens is that, unlike what happens in independent percolation, they are of a different nature. So IU and VU are different, and it comes out of a theorem from a paper which appeared of two papers. First paper that appeared in 2010, and a second paper with Vladas Sidoravicius, which appeared a year earlier. And then what one knows is that IU is always connected. So on the other hand, and it's an infinite translation invariant. And on the other hand, for VU, so there is a non-degenerate critical guy, U star, such that for U less than U star, well, there are not so many clouds, so many trajectories that fail on space. Well, VU has an infinite component. And if you take U bigger than U star, has all components finite. So there is a critical value U star such that if the parameter U goes beyond U star, that collection of trajectory becomes a kind of cloth because it's connected, it's some fabric, and it's insulating. And there was enormous effort into studying IU and VU, and there are many results that went on, but you can get some of this in two monographs. So there is a first monograph by Czerny and Teixeira, so Augusto is in the audience. And there is another monograph by Drewitz, Rat, and Sapochnikov. There, and if you go there, you'll see a lot of other results, and there are many crucial results that came from various researchers, and Sergei Popov is here, but there is also definitely David Belius also, and Zindisch, Tikeson, and many, and I'm forgetting quite a few of them. Okay. So that's the basic fact, but after comes the finer study of these percolative properties, and there are some critical values. Okay. So the situation, so I'm cutting corner, I don't want to tell too long a story, but in essence, what happens is that you have this U star, and you have two other guys. One is the U star star, and the other one is the U tilde, and essentially U bigger than U star star, it corresponds to strongly non-percolative regime. For VU. And I can even give you what's the definition of that U star star. So U star star is just as the smallest U, such that if you are taking along subsequences, well, you can find some subsequences of box such that the probability of going from the box of radius L to the boundary of the box of radius 2L, so this is 0. So it's a threshold beyond which, if you go from the L to 2L thing, so, and you are in VU, so along some subsequence, this is tending to 0. So it's known that if you go above that U star star, well, things are strongly non-percolative for this vacant set, in the sense that actually the probability to the strongest results there, it was a sequence of results there, and the strongest to date is in the work of Popov and Teixeira. But it's known that in dimension bigger or equal to 4, you have exponential decay with the distance of the probability to be connected from a point to a distant point. And in dimension 3, there is a logarithmic correction which is there. So on the other hand, so if you are taking the U, which is less than U tilde, here, so there is VU is strongly percolative. And I don't want to give the precise definition, but the fact that here you have, it's a strictly positive guy, and which ensures below the fact that you have this strong percolative property, This is an important paper of Drevitz, Rat, and Sapochnikov from 2014. There were previous partial work from Teixeira, but here somewhere it was an important fact that it could go to very small dimension 3 and 4 in particular. Okay, so here are these guys, and what is very plausible is that actually the way these guys are defined, they are just and one same person. So so it's a question. All right, but so let me get back to the kind of questions. So let me get back to the kind of questions that I've had in my motivating problems. How does that fit in? So so let me start with a result corresponding to VU for U, which is in strongly percolating. So, and that actually, so that would be U less than U tilde, but actually, the way I'll state the result, U less than U star star is okay for what I'm going to say. So what you want now to look at is a kind of problem which is of the flavor of what I've mentioned here, but instead of working with the random walk starting from the origin, you are going to start with the random interlacement at level U. So you look at the probability that VU, that Bn is disconnected from infinity by the random interlacement at level U by IU. So you cannot go from this large discrete box to infinity inside the vacant set at level U. And I'm having U less than U star star. So the result is consisting of both an upper and a lower bound, and it's saying that this is bigger than minus square root of U star star minus square root of U times the capacity of B, and B is this model compact set, and as an upper bound it's minus square root of U tilde minus square root of U squared times the capacity in RD of B. So of interest is the fact that I wrote it with lim sup and lim inf, but actually if the plausible thing that all these exponents are the same, well, this is really the limit. So the upper bound and the lower bound are the same. And so it means that somehow the kind of, I'll come back to that, but it gives a special kind of interest to the kind of how you get the lower bound in terms of understanding what the interlacements are doing in order to do this disconnection. So I'll come back to that in a minute. So there is here something which is also worth noting. It's the fact that if you let U become small, so U becoming small in that picture, it means just essentially removing all trajectories. So you are trying to disconnect a large box out of thin air. So it should be very costly. Well, it's not. So you see, when you let U tend to 0, the terms which are here are having finite limits. So when you try to disconnect a box out of thin air, you obtain something. Well, and this is very related to the fact that now for simple random walk, if you are trying to have the simple random walk disconnect a large box from infinity, well, this is, here there is a factor 1 over d coming out of the, that I forgot, coming of the relations between discrete capacities and the continuous capacities, but you obtain minus U tilde over d on one side, and on the other side you obtain minus U star star over d, the capacity on RT of b. So again, the thing is that if these critical values do coincide, well, you have somehow the lower bound and the upper bound here are the same, and you have pinned down what's the principal decay of that probability. At any rate, these values that you are having here, so there is a plus factor that comes out of the fact if you were for some reason above the level U tilde, but at any rate, what these gives you is that the decay, the scale of the decay is really exponential minus nd minus 2 times something which is a capacity. So this is what's coming out. Okay, so I want here to say a few things about that. So first, it's the fact, so maybe I should quote here. So here, so this is in a paper by Shinili and myself that appeared in 2014. This is something which is coming out of a paper from last December, a preprint from last December. This here is something which is from a preprint by Shinili from last December, and this is in the same paper which is there. The lower bounds follow a very different from the upper route from the upper bounds. So the lower bounds, they go under a kind of method which is called the change of probability method. So you implement a strategy which is producing an effect. Now, I won't have time to go into what kind of strategy you use, but the interesting feature is that for these lower bounds, the strategy you implement is doing the right thing for the wrong reason. So you are implementing a strategy which is somehow forcing a certain type of occupation time, and there are many ways in which the kind of walk could do a certain occupation time profile. In particular, it could slow down its motion. It turns out it's not the way it's doing it, and the way it's implementing it is when forcing some of these bumps, actually you also force disconnection. Of course, you have produced in that fashion a lower bound which is a priori not so related to the event that you had at first. So it even puts at stake whether you are on the right track. So the marvel is that actually, especially if these exponents are the same, you have an insight into what the walk is doing. Okay, so I want to say a few words about the part of the upper bound because it was stuck for a while. For the reasons I just explained to you, somehow the lower bounds were not really getting directly an insight of what happens if you disconnect. The other thing that I should say is that the upper bound which is here, so this is easily obtained from the first upper bound, so this upper bound is easy to obtain from this one by the fact that, well, you can couple the random interlacement IU conditioned to contain the origin with the trace of a simple random walk. And once you do that somehow in such a way that I is contained in IU. And once you do that, essentially you can dominate what happens for the simple random walk in terms of what happens for random interlacements, which have a bigger kind of structure, and then you can let U go to 0. Of course, this conditioning event that you are using here, that 0 contains, that IU contains 0, is having a vanishing probability, but things are done in the right order and you are able to retrieve the bound which is there out of that. So somehow the heart of the matter as far as upper bound were concerned was that. And I was stuck for a while there, and it was not clear that it was a happy story unfolding. And the savior came as Gaussian free field, yes. So Gaussian free field came there. So GFF. So GFF came under the heading of, well, there is something which is close to these considerations, which is an older story actually, which is the level set percolation. So you have phi, which is a Gaussian free field on ZD, and you are looking at the set where your Gaussian free field on ZD is at a level which is above H. Now, so this kind of problem, knowing whether this set percolates or does not percolate, has a long history. And I think Stas Molchanov is maybe in the audience, but there was definitely there was Molchanov and Stepanov, and that, yes, he's here. So that goes to 83, goes back to 83, and after there was first Leibovitz and Saller, 86, then Bricmont, Leibovitz and Mace, and there were quite a few players. And things got stuck for a while, but somehow it took a new kind of life recently when there was a feel that the methods that could be used in this kind of questions of looking at the percolative properties of VU, well, they could somehow apply there again. So, and there is definitely, I should quote that, so there is quite a few, but Rodriguez, and there is Rat, Popov and Rat, and Drevitz and Rodriguez. So there was a kind of new angle to get onto this kind of problem. Now, somehow the techniques were working on both sides, but somehow the nature of the link got deeper and deeper. And that came with this isomorphism theorem. And there again, it's a kind of a story, but which I don't want to tell into detail, so I'll be short. There is in the background a paper that I wrote here in 2012, but there is a result, a theorem of Titus Lupu, in a preprint from last year, which is showing that the link of the two models is very deep. Because what happens is that with this intensive use of the cable system, you have the fact that there exists a coupling of IU and the Gaussian free field, such that IU is contained in the set where phi here is strictly less than square root of 2u. So you can couple a random interlacement at a level u, which is positive, with a Gaussian free field on ZD in such a way that you have the random interlacement which is fully inside the set of points where the Gaussian free field is below level square root of 2u. And of course, in particular, this implies that the complement here, the vacant set of the interlacement, so this is containing the set of points where the Gaussian free field is above square root of 2u. So, so that somehow induced a very deep link of the two models, and in the parallel story that you can write here for the Gaussian free fields, well, parallel to these guys, so you have an H tilde, and you have an H star, and you have an H star star. That you can define, and here what happens is that when you look at the set of points where phi is above H, so when H is above H star star, it's strongly non-percolative. But when it's below that, H tilde, it's strongly percolative. And the H star corresponds to having the threshold where there is percolation or not. And so the results here could prove a number of properties about these regions. But just what I just want to point out is that these couplings have also a significant power into them, because out of this you can link what is known about random interlacement to what is known about Gaussian free field. And in particular, you have the fact that the H star is less than the square root of U star, which comes out of that simply, if that guy does not percolate, certainly that guy is something which is not percolating here. So you have something of that nature. You also have the fact that if you are looking at this inclusion, that IU is contained where in the set where phi is less than square root of 2u, well, this set has the same kind of in distribution. It's the same that where phi is something which is big or equal to minus square root of 2u. So it means that if you are looking at a super level set of the Gaussian free field above a negative value, it contains in it this connected piece of cloth. So out of that you retrieve this inequality free of charge. So this inequality was obtained by Brikmont, Leibowitz, and Mace by an interesting argument that has to do with maximal external contours, that was related to what Wendelin was talking in the first talk, and somehow there is a lot between the two models, and the full extent is still not known. So in particular, the understanding of constructing the whole families simultaneously of the full level sets of the Gaussian free fields and of the interlacement, it's still unfolding. Let me say that here, so again, in that story, it is plausible that these guys are just one guy, but that remains to be seen. And what I should still say is that, for instance, here one knows that H star here is big or equals to 0. There is H star strictly positive is believed to hold for all d big or equal to 3, but so far it's for high d. It's shown for large d. And actually in the paper of Drewitz and Rodriguez, so that was shown in that paper from 2013 with Pierre-François Rodriguez, that for large d it's positive, and actually there is the equivalent, so the behavior, the equivalent of that value H star, which is blowing up like square root of 2 log d, which is shown by Drewitz and Rodriguez in a paper that appeared this year. But it's believed to be true for all d bigger or equal to 3. The proof is still missing, and there is a serious obstruction in the type of argument which was used in the paper of Brikmont, Leibowitz, and Mace, and which is also related to the fact that if you are looking on the cable system, so you interpolate with something which is continuous sticks, then in that case you don't have positivity. The critical value is 0, as shown by Titus Lupu. So okay. So as I said, I don't want to go too much into this the story. It would take me too long. Quite a bit happened, but what I want to get back to is the fact that somehow to get to the upper bounds that I mentioned. So model of the Gaussian free film and level set percolation was very helpful because the Gaussian free field enjoys some nice properties. In particular, there is a Markov property which is playing a crucial role. So here, in some sense, the problem one looks at is one has this box Bn, which has centered at the origin and the size of order n. And one has a much larger box here with the boundary, which is Sn, which is the boundary of the box, which is a multiple of that box. And one takes an H such that phi H is in the strongly percolative regime. So that means H less than this H tilde I was mentioning here. And you are trying to look at the phenomenon that there is no way. So normally there should be a way to go from Bn to the boundary of the box with remaining in the set where phi is always above level H. But you are looking at the case where there is a kind of blocking interface where phi is less than H. And what you are interested in is the probability that you are blocking the possibility to go from Bn to this boundary Sn above level H. So this is the appearance of such an interface that you are trying to measure. And the result here is that 1 over nd minus 2 log of that probability. So there is a lim sup, lim inf in n, and this is minus 1 over 2d h tilde minus, so I'm taking yes, squared times the capacity on Rv of v. And here, this is bigger or equal to minus 1 over 2d h star star minus h squared cap on Rv of b. So you see, it's something which has a very close flavor, except it's not. There are some differences because here you have a naive square, there you don't have a naive square. But you have something which is close in spirit as a result. And again, if the plausible equality does happen, so you do have the fact that the lower bounds and the upper bounds which are there are just the same, and this is a limit that you are obtaining. So attached to that and to the kind of strategy which happens inside the proof of the lower bound, you have a kind of phenomenon of entropic repulsion that is behind that on the strategy on how you produce such a disconnection. But I don't have time to go into it because I just want to give you a snapshot of how you get to the upper bound, which is the first step in how you get to the upper bound which is there, which was a stumbling block for a while. Okie doke. So. Oops. so sketch of upper bound. Okay, so the idea goes roughly as follows. So you have Bn, which is here, and you have your Sn, which is like this. And the idea is that you are going to draw columns so you do that in all these faces, which are columns made of small boxes. And these columns are linking Bn to the surface. So here I'm blowing up this small box here, so it will be D, and I'm surrounding it by an even bigger U, and the size of the guy which is here is L. So this is this L after blowing up the picture, and L is something like n to the n log n to the 1 over d minus 1. Okay, so one of the important properties of the Gaussian free field is that you can decompose it here, so you can write your phi as being an h u plus a psi u. So you have something which is an harmonic average of the values of the Gaussian free fields on the boundary of the bigger guy. So u is something which is much bigger than this d, but it's a multiple of that size. And so this is harmonic average. And this one is a local field. Which somehow vanishes outside of U. The strength of this decomposition is that these two guys are independent, and you have the fact that it's the local field, so psi u and psi u prime are independent if u is not intersecting u prime. Okay, so the rough strategy of the proof goes as follows. It's using the fact that if you are taking the u large, this psi u is approximating the Gaussian free field. So the percolative properties of phi, you can somehow transmit them to this local field, and you have the fact that psi u here bigger than h tilde minus epsilon, this percolates well in D, and except with super polynomial decay. Of probability. Now, once you have that, you can start to look at the various columns that are here, and you have the fact that except for few columns, most of them have no bad box in that, so in the sense that this would not hold. So these are the psi good box. So Now, except with a exponential minus constant nd minus 2, you have few columns have a bad box. A psi bad box. So that means most columns are just made of good boxes at the level of the local field. On the other hand, you are blocking the fact of, this is what you're trying to estimate, you don't want that there is any connection going from Bn to H. So if the local field is good everywhere and you can somehow connect, the only way you can make sure that something like that happens is that there is a box where the harmonic average is getting too low to block. Okay? So that means that to block, so you must have an HU which is getting below something which is minus H tilde minus H, in order to lower the set to a region where the level sets of the green function of the Gaussian free fields is in a non-percolative mode. So you lower yourself to somehow be in a rarefied kind of region. So you must find some box doing that in most of these columns, in all but few columns. And then what happens is that you are in a situation where you now can choose. So it's a coarse graining step. So you can choose some boxes where this harmonic average is getting below this level in most of these columns. And on the other hand, the number of choices, so you choose a collection of boxes with HU, which is minus H tilde minus H in D. And what saves the day is that the choices of the scales that I've mentioned make that the number of choices of C is not too large, and on the other hand, by Gaussian estimates, you can have good bounds on the probability that for all these D in this collection, you have the somewhere in D, so you have a value which is less than that. And this by Gaussian estimates of the type Dudley-Fernick and Borel TIS estimates, well, you are able to control that very well, and that brings the capacity into play. So that brings something which is like exponential minus and a capacity h squared over 2 times the capacity of C plus something which is O of ND minus 2. And the combinatorial complexity of the choice of C are negligible with respect to this exponential factor. The last trick that comes is that this kind of floating finite collection of boxes that you are choosing in each of the columns, well, you can see that the capacity of this, it's the capacity of the union of these D for D in C. So the capacity of that guy, you can somehow estimate both by a projection argument plus a kind of winner test in order to see that this is something which is at least ND minus 2 times 1 over D cap of the ball, or it's N cap of Bn in essence. So there is something, because you deleted some boxes and you deleted some columns, but there is a kind of projection argument that enables you to somehow retrieve the capacity of Bn, and once you have that by approximation, you have 1 over the continuum capacity. So this is rough, of course. It's kind of, I just give you a flavor of the type of argument, but this is somehow what saves the day for the Gaussian free field. And then it's another story to get it to work for the random interlacement, but it still gives you an important flavor of what's the nature of the argument to get the upper bounds. Okay, and I'll stop.
So there is time for a few questions.
Yes?
I have more of a comment to the connection of the Gaussian free field and the trace of the random walk was also exploited in my joint work with Jan Ding and James Lee in 2010.
Yes.
Which is a little different because it's one random walk, not interlacement. But in particular, the same idea as the Lupu was recently used by Alex Zhai to refine our results from there, again following Lupu.
Yes.
So that idea of using the cable process seems very powerful in both.
Yes, indeed. Yeah.
More comments or questions? So, then we thank again